Afternoon, ladies and gentlemen. I'm Jon Claerbout. I'm semi-retired. I wouldn't be here now except I've run across an interesting story I'd like to tell you, and solved an old problem that's been bugging me for years. About 25 years ago, I went to visit a gentleman who had a sparker system in a harbor, and he had the job of finding the rocks and finding the gas pockets. And he showed me his seismograms, and I was just amazed and delighted to see that with his color printer, the rocks all turned out red and the gas pockets all turned out blue. And so it made me wonder why it is in seismology we can't routinely recognize the polarity of the signals we're looking for. Well, I didn't want to cook up an ad hoc method, but I fell upon recently a fundamental method, which I'd like to tell you about, and I've enjoyed working with it. So let's get started. The title of my talk is not exactly the one that's in the report. The newly revised title is Mostly Causal Deconvolution Clarifies Marine Seismogram Polarity. So here's the usual Ricker wavelet, and this is what we usually see in marine data. And the reason we usually see this is because the shots are underneath the water, and there's a ghost. And there's a wave goes up, hits the free surface, turns around, comes back down with the opposite polarity. And this happens twice. It happens once near the shot and once near the receivers. The receivers are also underneath the water. So more or less, this is your direct arrival from, and this is your water. There's two rays that have this path that have one surface bounce, and the rays that have this path have two surface bounces. So in industrial standard deconvolution, you try to make a pulse come out right here. So you've got this convolution filter coming along, and you're trying to produce a pulse here, and then you're trying to produce nothing as you go across the rest of it. Now, what I'm trying to do is I'm going to try to produce a pulse here, so my filter will come along and try and produce nothing as all this stuff goes through it. And then it'll suddenly here it'll try to produce something, and it'll try to produce nothing as we go on. So what I want to do now is show you a movie. I'll fumble around a little bit. We're getting this set up. Ah, good. There's the movie already. So what we have here to begin with, you can see if I can enlarge this a little bit. What we have to begin with here is a causal wavelet. This wavelet. Okay, so I started. I got 1,000 traces from the Gulf of Mexico, and I computed their power spectrum. And now with it, I'm going to create a whole bunch of wavelets with the same power spectrum, but they're going to have a different phase spectrum. The very first one shown is what is a causal deconvolution. This wavelet vanishes before time t equals 0. What you can see is it does not look like a Ricker wavelet. At a later point in time, we have what's called a bubble. Then there's some additional bubbles at 2 and 3 times. Now what I'm going to start doing is allowing coefficients to vary in front of this bubble, and then you'll see what happens. And I'll be explaining this, of course, as I go on along. So I'll put the cursor right near where the first digital point probably is. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Say maybe 10 points. I can keep going. Maybe 40 milliseconds if it was 10 points. And so now you can see we basically have a Ricker wavelet. This stuff here is probably wrong, and the bubble is still on this side. If I asked for a totally symmetrical response, then we'd have a bubble over here, so we don't want a symmetrical response. We've got a nice phase response. So anyway, this is the kind of answer I'm going to be giving you, and you get to choose which one of these many answers you would like. And I think that it's not terribly critical. Once you basically know this length, you can sort of accept any one of these answers here. This is the one parameter you choose. I'm going to give you an analytical solution with that one parameter that you choose. this is just a little more detailed picture of this thing I showed you. There's 101 seismograms, near trace seismograms from the Gulf of Mexico. Here's the first bubble, second, third, and fourth, and here's the Ricker wavelet where you can actually see the individual points. So what happens if we divide this waveform, which you just saw, we divide it out of some data. This is a different set of data. I hunted around, found an interesting set of data, really old set of data. These shot profile number 33. Now, what you know is true on here is that each one of these has a different polarity, because these are multiple reflections of very high order. But it's not very apparent that they're changing in polarities. We don't have red and blue, red and blue, red and blue. Now, after this simple process of estimating the correct wavelet, you get something where you can see black, white, black, white, black, white, black, white, black, white. If you come down at an angle, you can see black, white, black, white, black, white, black, white, black, nothing. So that's the kind of answers you can get, and that's the first try. I just figured out the one parameter analytically. I didn't play with it, and that's what I got for answers. There's ways to make it better and other ways to do things, but that just shows you what you can get. So why does this work? The reason it works is if you have the right wavelet, if you deconvolve, simple as that, the polarity is going to become clear. The name of the game is getting the right wavelet. Why does conventional deconvolution fail? Well, Ricker wavelets do not have a causal inverse, and that's called minimum phase, is another statement which means does a causal wavelet exist, and the Ricker wavelet does not have a causal inverse, so naturally the traditional method has difficulty. Okay, well, in the old days, I'd come to SEG meeting and everybody would be talking about deconvolution. There would be half a session of people talking about imaging. Nowadays, it's just the opposite. You go to SEG, everyone's talking about imaging. I don't know if anybody's talking about deconvolution, so I need to remind you of a few things. There's three terms which roughly mean the same thing: blind decon, predictive decon, causal decon. And the industry has a big history with lots of names. It's fun to tell all these stories. It represents actually much of my lifetime. They're a big investment of my graduate student days. And they come up with a method, which we might call the Wiener method, which is in the time domain, and the number of computations is n squared, and nobody cares about the n squared because that's so fast these days. It's a one-dimensional problem. In my textbook, there's another method, which I call the Kolmogorov method. It's faster. It's in the frequency domain, and that's what I'm going to do today. I'm going to adapt the Kolmogorov method to what I'm calling the mostly causal inverse, examples of which you just saw. I would do this in the industry standard time domain if I knew how, but I don't. I only know how to do it in this frequency domain, but it's fine, and it works good. It gives good answers. Here we have the Hilbert transform. You have a real signal. You put in its even part on the top. If it has an imaginary part, you put that here. And you put its odd part here. The real odd part would be here, the imaginary odd part would be there. We're going to do a Fourier transform. We're going to do a weighting function, and we're going to do another Fourier transform, inverse Fourier transform, and you'll end up with some signals over here which have real and imaginary parts both. Basically, the basic thing about Fourier transforms is that the even parts, these are even parts, they just transform to even parts with a cosine transform. It doesn't matter if it's imaginary, it transforms to an imaginary even part, but the odd parts change over, and it changes from a real odd part, we'll do a sine transform into an imaginary odd part, so the odd parts cross over. Now what's happening in the middle? We're multiplying by a step function that vanishes before t equals 0, and after t equals 0, I'm going to multiply by 2, because if I multiply by 2, I preserve the real part. So the thing that we start off with will be the same thing that we'll end off with here. And so we go through this process, which is called Hilbert transform. Out comes an analytic signal. We have the real part, the imaginary part. The imaginary part is a 90-degree phase shift of the real part. Okay, now this talk that I'm going to give has only 3 equations, and 2 of them are on this page. The first one says that we have an S bar, which is a positive number, and it's equal to e to the log S bar. And this is because exponential and logarithm are inverse to each other. And this would be actually true if S bar was a function of frequency. And the second equation, equal sign, simply says U bar is log of S bar, and that's simply a definition of U bar. The third equation says we're going to hook up some imaginary phase. We don't know where we're going to get it, but we're going to have it. After we have it, we're going to call it e to the u instead of U bar, and we'll call it S instead of S bar. Hilbert transform was the kind of thing that operated down in the ground here, at the ground level with shot waveforms. Operating up here in the stratosphere, up in the exponents, we can also play around with things like Hilbert transforms, and that's what Andrei Kolmogorov did 40 years later than David Hilbert. Of course, David Hilbert was a pretty smart guy. I'm sorry they named him after this really simple process here, because he's really invented Hilbert spaces, which the physicists, nuclear physicists, atomic physicists really needed to have to invent their quantum mechanics. But anyway, we know him for this process of Hilbert transform. So this is going to be the shot waveform if we inverse Fourier transform it. And this Utah space is really strange. It's a strange space. We're not accustomed to it. We don't even have a name for it that is well known. I'm going to call it the lag log space, because that's what it is. We're in the logs. We got the log spectrum up there. We've transferred back to the time domain. So it's like looking at lags. You kind of think it feels like an autocorrelation, but it really isn't, because U bar doesn't have to be positive. So that's our parameter space where we're going to play games. Now, when Andrei Kolmogorov put this to work, he put this Hilbert transform idea to work a little bit differently. He put his log spectrum in here, U bar, and he's going to put in a 0 here, but you might put in something else. Sometimes you have complex valued traces. I don't have any complex valued traces today, but normally a signal is a real function of time, but if you Fourier transform the x-axis, then the signal becomes a complex function of time. But so you can see where that would go if you had it, but let's just follow a real signal coming through here. It's even function of omega, and here we are with U bar. It's a symmetrical function of lag, similar to an autocorrelation function. It's even. And this process brings us to a phase function. And some magical properties of this phase function, which I'll be telling you about, which Andrei Kolmogorov figured out 40 years after David Hilbert survived. And along the way, we get this, here's our lag log space. We get a causal function in lag log space. Okay, so we might thinking of how does this U sub tau relate to the shot waveform? And that's what the next slide is going to be about. There's a theorem which is, really Kolmogorov was the first. He published this in 1939, and during the war, which was right after that, Norbert Wiener also developed this, pretty much the same idea. So in the West, I guess it's known as Wiener's idea. So the basic concept they have, the basic principle, if I translate it into geophysical language, is if lag log space is causal, if our parameter space is causal, then the shot waveform is going to be causal as well. So I'm going to prove this for you. And once you understand this, you'll be able to understand that you're doing spectral factorization, and that you can do deconvolution by this method. And after we understand we can do deconvolution, then I'll show you how we can fiddle around with deconvolution to make it not quite causal, mostly causal, and handle those Ricker wavelets. So bear with me. If you lose track of what I'm talking about in this slide, try to come back for the next slide, because I'm going to prove a pretty abstract theorem here. If lag log space is causal, then the shot is also going to be causal. So we'll start with a time function, which is causal. By causal, I mean all the subscripts here are positive numbers. We have the usual definition of z equals e to the I omega delta t. Then you make a z transform by putting the U1 here, U2 goes here, and so on. And this Z transform is secretly a Fourier transform. You can sort of tell that because if you had Z cubed, there'd be like a 3 delta t. If Z cubed is 3 delta, so it'd be U3 e to the I omega 3t. So it's really secretly a Fourier series. And before I tell you how this works, I'm going to tell you my last equation of this talk is this one here. This is a Taylor series for exponential. It's very easy to prove this thing because you know the derivative of an exponential is the same exponential back again. And if you take the derivative of this term, you get that term. So it's easy to prove that infinite series there. Let's call this a polynomial because the data set will come to an end. Now we have to take our data set and we have to drop it in here. Just take a copy of this, drop it in there. And U squared, what is that? Well, you can either square this polynomial or you can take this causal function and convolve it onto itself. And U cubed means you take this causal function, convolve it onto itself 3 times. You add up all these causal functions, or if you look at the polynomials, what you discover is there aren't any powers of 1 over z. And you've manufactured a causal function. And furthermore, this thing always converges. I mean, we're finished now. We know there's nothing anti-causal about this e to the u. It's totally causal. That's what we were setting out to prove. A mathematician would go one more step and say this series always converges because the factorial is in the denominator. So, if you've been with me now, you know we've proven the abstract theory that was unknown to Fourier, unknown to Hilbert and Gauss and all those other old people. And we're going to put it to some use, and we're going to change it a little bit. Sorry, I should have taken those off earlier. And basically, the shot waveform is e to the u, and the decon filter is e to the minus u, so it's nicely parameterized. Now, what are the main facts you need to know about lag-log space? We're unfamiliar with this space, and we're learning about it. One of the facts is that if you have a large lag in Utah, that will affect only large lags in the physical space, in the wavelets, in the decon filter. Now, how do we know that's true? Well, just take, for example, this polynomial, 1 plus z to the 10th. If we're going to put that into e to the u, we're going to have to raise it, square it, cube it. If you square it, you got z to the 20th power, cube it, you got z to the 20th power, 30th power. You can never make z to the 5th power by raising this to high power, so that proves it. Large lags in u are definitely going to affect large and larger lags in the exponential. Now, the next part we need to know is not quite so easy to show. Small lags in our lag-log space affect mainly the small lags in the wavelet and the decon filter. Well, they will have an effect on the larger lags as well, but I'm not going to prove this, and you'll see examples of this. Just reminding you again that this is the space of e to the u brought into the time domain. If you saw u itself, it would be kind of similar. It would, yeah, that's what I'm saying. So the bubble is in large lags. In other words, here's the bubble. These are the bubbles. These are the large lags out here. And the Ricker wavelet is in the small lags. And the final fact you need to know, which is going to lead us up to the innovation, the actual innovation here, how I did my magic trick. We're going to be messing around with the small lags. We don't really want to believe causality completely. We want to take into account the Ricker wavelet. And what do we know about the Ricker wavelet? The thing we know about the Ricker wavelet is that it has no phase. So we're going to fiddle around a little bit with that part of it. So the innovation itself is quite simple. You identify the odd part of the lag-log space. You pretend you're going to do a causal deconvolution. Go ahead and get the lag-log space. And now start looking just at the small lags. And take those small lags of this odd part only. You can mess around all you want with the odd part because that's determining the phase. The even part is determining the spectrum. You can't touch it. So you take the odd part at small lags, just weight it down, and you can have a weighting function of your choice. I simply used a cosine weight. There may be reasons for some weights over another. I haven't looked into that. But that's going to give you the Ricker-like response at small lags. So, if I may repeat myself, why does this work? Because if you deconvolve with the right wavelet, the seismogram polarity is going to become clear. That's obvious. Just take you back to my first example again. I didn't have any parameters I needed to tune on my process. The first time I tried it, it worked. Now, there's many ways to estimate spectrum. I estimated a spectrum from 1,000 seismograms before I started. And now you can smooth that spectrum. That's one thing you can do. And there's lots of things you can do. You can have a filter which is not really long. I designed one filter for all traces. In this case, I didn't have, in this case, I didn't have 1,000 seismograms. I had these seismograms, just these 30. Probably there's 48 seismograms. I had 48 seismograms. Average their power energy spectrum or their log spectrum, average energy spectrum. And then I chose one filter, and the filter was the full length of the trace. Well, maybe you don't want a filter that's full length of the trace. Well, you can make shorter filters by smoothing in your spectrum, or you can make shorter filters by tapering in the lag log space, or you can even, I think you can truncate in the lag log space. There's lots of ways to do a decon, and there's more to decon than the process I described because you have to talk about estimating your spectrum. So what's good, we're now sort of at the conclusions here. What's good about this talk? What's good is that predictive deconvolution makes the assumption that the inverse source wavelet is causal, and that's not true for Ricker wavelets. And the consequence of that is that marine seismology is ripe for a revolution, after which people should be able to, geophysicists should routinely be able to recognize the polarity of what they're dealing with. And this is a good, if you're doing an optimization problem in inverse theory, something more sophisticated than this is a good starting solution, and it's also a good regularization. And optimization theory nonlinear optimization theory often needs a regularization and a good starting solution. So that's what's good about this. There's a few bad things about this. This makes the false, like all the classic deconvolution, it makes the false assumption that a white output is desirable. It also ignores the fact that there's sparseness in many real geophysical signals. We have strong reflectors and we have weak reflectors. And it's not uniform. And it also makes the false assumption that echo data can be gained before filtering. The data I showed you is multiplied by t squared to bring up the late times. This is an assumption that's commonly made in industry, and this assumption should not be made either. So more sophisticated theories, as in my other talk, will correct these issues. So that's all there's to the story. I thank you for listening to it. And the code is in the article, and it's a change of the textbook code of only 6 lines, so I hope you'll try it, and I hope you'll enjoy it. And if you make any examples, I would like to see it. So thank you very much.